Okay, so for our first example, we have two spheres are launched horizontally from a table 1 meter high. Sphere A is launched at 5 meters per second, and sphere B is launched at 2.5 meters per second. We want to know how long does it take for each sphere to hit the floor? B, what are the distances that each sphere travels from the edge of the bench? So, we've got some kind of table or bench. There are two spheres here, a red one and a blue one. Call that one A. And then behind it is going to be B. Okay. Now, both of these spheres are launched off of the table at the same time. Okay. One has speed 5 meters per second, the other speed 2.5 meters per second. So sphere A is launched 5 meters per second. We'll assume it's going to go farther. It's going to undergo projectile motion. Sphere B, not as far, but we don't quite know how far just yet. We'll just kind of see how that is. So let's start to sort of set up the problem that we've got here. Okay. Sphere A, we know something about that. All right, sphere A is launched at 5 meters per second. So B naught is 5.0 meters per second. All right. And it's all x direction, so the x component of the velocity is 5.0 meters per second. Nicely enough, if it's all that, we can see too what the vertical initial velocity is as well. If it's shot off horizontally, and this is the vector that represents it, then Vy initial is 0. Okay? That's a great initial velocity to have. Okay, so we know this about the second ball. The second ball, sphere B, is launched at 2.5 meters per second. So we can do the same kind of analysis here. Right? B naught for B, so B naught for A. Make sure we know these vectors. Is 2.5 meters per second. And in an analogous situation, it was shot horizontally, so that is the x component of the velocity. It's the velocity through the whole motion of that ball. And we can say that Vy naught for B is 0 as well. We'll make sure that we've got track of things here. So we've got Vx for A. So this is what we know about the horizontal direction right now. We also know something about the vertical direction. That y is equal to 1 meter. Now again, if you're the person standing here watching this, you just see both of them drop, right? We'll orient ourselves, we'll just say that y naught is 0, and y down here is, well, that 1 meter. Now, again, think of what connects these two situations. You have two balls that are going up the table. This person here, if you ask him, which one is going to hit the ground first? Exactly. He sees both of them just drop straight down under the influence of gravity alone. They're going to hit the ground at the same time. So that's the thing that's going to connect these two. Right? The time for ball A is going to be the same as the time for ball B. Right? So let's find out what that time is. With this information in the x direction, we really don't have much to work with, right? We know its x position in the end is going to be its velocity in the x direction times the time. Put your a's and b's there, it's the same equation. We know that this is the same for both of them. So this is the one we need to find out this distance. How far away from the edge does each lord hit? But we'll notice we have to solve for the time first. And in doing so, we're going to have to take a look at what is happening in the y direction. Well, in the y direction, it looks just like these are going straight down. So let's take our equations for the y direction, and we'll see that the one that's going to be most beneficial for us is going to be y equals y naught plus by naught t plus 1/2 gt squared. Now in this case, does it matter if I'm looking at ball A or ball B? No, they both fall through the same distance and the same time. They will have the same acceleration due to gravity and the same initial velocity. So let's just go through this. We decided that the initial position was 0. We decided that the initial velocity was also 0 in the y direction. And we're left with y equals 1/2 g times t squared. We're going to do a little bit of the algebra to solve for t in this case. We'll see that t is equal to 2y divided by g, and then take the square root of that there. So, putting in some numbers to find t, we're just going to have 2 times 1.0 meters divided by 9.80 meters per second squared. And we'll take the square root of that to find that the time for both of these balls to hit the ground is going to be about 0.451753. Right, 0.451753. Right, this is what your calculator gives you. Now this is the value we're going to have to use for our calculation of B to find out what the distances of each ball is going to be. So we're going to leave that in our calculator, save it as t or something like that in your memory function. We're going to round it for our answer, so we'll say the answer to A is t is equal to 0.45 seconds. Now we can use this information to analyze motion in the x direction. So, note that this is the time for both of them, okay? So we're just finding out, alright, how far did they go in this time? So for ball A, the new position of A is the A times t. I'm not going to put the a there because we don't need to distinguish at this point. So x of a is equal to the velocity of a, which we said was 5.0 meters per second, times the time, which we just calculated as 0.451753 seconds. Right? When we do so, we get a value for x of a is going to be 2.25876 meters. We'll round that up to x of a is equal to 2.26 meters. Now, what we'll notice is that sphere B is launched at 2.5 meters per second. And we can do some quick analysis of this and see that the velocity of B is 1/2 of the velocity of A. So when we look at what we've got here, x of B is VB times T. XB then is 1/2 VA times T. So, in that same amount of time, B can only go half of the distance. Right? Don't have to do much calculations here. All we have to do is find our last value that we got, divide this by 2. Technically, we should use this value, but I want to do it in my head, so it'll just be 1.13 meters. And that's how we're going to be solving these problems. Alright? We knew we had to use this for the x direction, but we did not have enough information. All we had was the velocity, we didn't know the time. This is very characteristic of questions like these. So, what we're going to do, if we don't have enough information from the dimension that we're interested in this case the x component of the motion, we need to look to the y component and see if we can get the information that we need, the time in this case, to fill in what we don't have in that dimension.